Bismillahirrahmanirrahim. This is lecture 4 on the magnetic field and the vector potential and the Biot-Savart law. We start with Gauss's law and magnetic flux. Since the lines of flux are closed, then application of Gauss's law to a closed surface gives psi m equal to integration over a closed surface of B dot ds equal to 0, which implies that the divergence of B is equal to 0 according to the divergence theorem, when we transform the surface integral into a volume integral for the divergence. So this is Maxwell's first equation for magnetic field. Now we consider Ampere's circuital law. If we go back to Ørsted's experiment, as we have seen in the last lecture, for a straight wire, B was in the direction of phi equal to mu naught I over 2 pi rho. If we calculate the circulation integral around the circle of radius rho, we see that the circulation integral of B dot dl is equal to integration from 0 to 2 pi of rho b phi d phi, which reduces to mu naught I. This is Ampere's circuital law, which is the line integral of the magnetic field is equal to mu naught I. This is the integral form of Ampere's law. Now, to find the point form or the differential equation of Ampere's law, we use Stokes' theorem and replace the current by the integration of the current density over the cross-section of the wire. So I is integration over S of j dot ds, where S is the cross-sectional area of the wire. So Ampere's law becomes integration over S of curl B dot ds equal to mu naught integration of over S of j dot ds. So this leads to curl of B equal to mu naught J. This is Maxwell's second equation for the steady magnetic field of the steady electric current. Equation 1 implies that B is the curl of a vector A, which we call the magnetic vector potential. Thus B is equal to the curl of A. If we insert this into equation 2, we have the curl of A equal to mu naught J. Now we can use the vector identity for the curl of a vector, which gives curl A equal to gradient divergence A minus del square A, the Laplacian times A. We have gradient divergence A minus del square A equal to mu naught J. Now we look at the principle of duality between electric fields and magnetic fields in order to be able to find the governing equation for the vector potential A. If we look at the electric field of the infinite line of charge, we find that E rho is equal to rho L over 2 pi epsilon rho, and the line was extended along the z-axis. For the infinite straight wire carrying a current I, the magnetic field was in the direction of phi, not rho, but equal to mu naught I over 2 pi rho. So mathematically they are the same. The only change is that epsilon becomes 1 over mu naught and rho L goes into I. Also, another example is Coulomb's law for 2-point charges. The force between 2-point charges, Fe, is Q1 times Q2 over 4 pi epsilon naught r squared. Now, if we take two magnets and we space them a distance r apart, if the pole strength of magnet 1 is Q1m and the pole strength of magnet 2 is Q2m, then the force between the magnets has the same form as Coulomb's law for the electric charge, and we get mu naught Q1 m q to m over 4 pi r squared. In order for this to be true, the governing differential equations of the electric and magnetic fields should be mathematically the same. The governing equation for the electric potential is Poisson's equation, del square V equal to minus rho V over epsilon naught. So we expect that the magnetic vector potential will satisfy Poisson's equation, but for a vector, not a scalar. For any vector to be completely specified, this is Helmholtz's theorem, we need to specify both the divergence and the curl of the vector. Since the curl is specified by curl A equal to B, we choose the divergence to be 0, divergence A equals 0. So if we do that, we immediately get Poisson's equation for the magnetic vector potential. Okay, and this choice is called the Coulomb gauge. The Coulomb gauge because the fields are similar to the fields in electricity for using Coulomb's law. Now the solution of the scalar potential is this integral without any mathematics. It's just from physics. V of r is 1 over 4 pi epsilon naught integration of rho v dv divided by the distance r minus r prime. So similarly, the vector A will be equal to mu naught over 4 pi integration over the volume of j dv over r minus r prime. Here j is a volume current density, now if the current flows on a surface, then the current element j dv becomes k ds. So we use k or js instead of j, and js has units of amperes per square meter. J has units of amperes per square meter, but K or Js will have units of amperes per meter. It's a current per unit width. If the current flows in a filamentary conductor, in a wire, then JdV becomes IdL. So A of R now for a filamentary conductor will be mu naught I over 4 pi integration around the path of the current, the closed path of the current, the circuit, dl, the element of length, divided by distance r minus r prime. Now the b is the curl of a, so if we take the curl of the integral, we know the del operator is a differential operator with respect to the space variables here, r or x, y, and z. Okay, so we take the curl of dl over r minus r prime with respect to the field point variables. If we use the vector identity for the curl of a vector multiplied by a scalar, we see that curl f times f is the gradient of f cross f, that is gradient of the scalar cross the vector plus the scalar f times the curl of the vector. Now the vector here is dl, so if we take the curl of dl, we will see that it is equal to 0. It is directed along z, and from the expression for the curl using the determinant, the derivatives will be with respect to x and y, and they will be 0 because this is in the direction of z and it is a function of z. So we will be left with gradient of the scalar cross dl. Now the gradient of 1 over r minus r prime we have seen before. The distance is the square root of x minus x prime square plus y minus y prime square plus z minus z prime square. And if you take the gradient, it becomes the vector r minus r prime divided by the distance cubed with a minus sign because it is in the denominator. Now we get rid of the minus sign by reversing the order of the vectors, and then B will be equal to this. Now for a current element, B becomes dB, and we have dB equal to mu naught I dl cross r minus r prime divided by 4 pi is the magnitude of r minus r prime cubed. This is the Biot-Savart law for the current element, and it is the basis for calculating the magnetic field for different current distributions, which we will be taking in the next lectures. Note the difference with Coulomb's law for an element of charge. Mathematically, they're the same except for the presence of dl instead of dl as a scalar in Coulomb's law for the charge, and there is the cross product here. Okay, so this is the difference between the two formulas.